These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you. Do you know what the derivative of this function is?
4x to the third.
That's right. And what would be the symbol for that derivative?
F prime of x.
That's right. Okay, good. So let's figure this out.
Okay. 15x to the fourth.
Okay, very good. How about this?
This would be 1.
Okay, good.
Right.
Sometimes the simplest cases can be the toughest, so it's important to make sure you know how to do those. How about this?
That would be 8, I believe.
So the same as the function?
Right.
Okay. Now, let's review some terms here. So, two things that come up a lot in math are constants and variables. So, for example, what is this number 4 here? A constant or a variable?
It's a constant.
How about the x?
Variable.
All right. How about this?
Constant.
And the x?
Variable.
And the 3?
Constant.
Okay, good. Now, you have to keep in mind that letters don't always stand for variables. Sometimes a letter is used to stand for a constant. Usually, we use letters from the end of the alphabet for variables, and usually we use letters from earlier in the alphabet for constants. So a letter could be either a constant or a variable. Okay, so now, going back up to, so here we're figuring out the derivative. Maybe let's try this example here. Actually, let's try this one. What's this derivative?
This would be 6.
That's right, 6. Okay, what does that mean? So far I've just been giving you a bunch of derivative problems, but I haven't asked you what the derivative means. What does this number 6 tell us about the function?
The slope of the function at 1 is 6.
I'm not sure where you got the number 1.
Okay.
So we're doing this example here now.
Right, right.
So the number 1 wasn't involved here. So try again. What does the number 6 tell us?
The slope.
The slope of what?
The slope of tangent line.
The tangent line to what?
To the function 6x.
Okay, good. So that is one good interpretation. One good interpretation is that the slope of the tangent line to this curve is 6. That's right. Now, there's another important interpretation, though. Why do we care about that slope? The derivative tells you how much the function will change if you change the independent variable. The derivative tells you how much the function will change if you change the independent variable. So, for example, in this case, it means if we increase x by 1 unit, the function will increase by 6. That's the meaning of derivative, and that's why we care about the derivatives. So what this means is that when we increase x by 1, the function will increase by 6. Now, actually, it's a little bit more subtle than that, because usually the derivative only tells you the approximate change in the function. Usually the derivative tells you the approximate change, but in this case, it gives you the exact change because this curve is just a line.
Okay.
So when you have a line, the derivative gives us the exact change. Otherwise, the derivative gives us the approximate change. So what does this number 6 tell us? It tells us that if we increase x by 1 unit, the function will increase by 6.
Okay.
And I think you, in fact, know that that's true. For example, when x is 0, what would the function be?
The function would be 0.
And when x is 1, what would the function be?
6.
And when x is 2, what would the function be?
12.
And when x is 3, the function would be?
18.
Notice that when we increase x by 1 unit, the function really does increase by 6 each time. So the derivative told us true information in that case. Okay, so let's try another example. What's f prime of x here?
This would be 3.
Good. How do you interpret that? What does that tell us?
If the value of x increases by 1, then the function increases by 3.
That's right. Every time we increase x by 1, the function increases by 3. And if you plugged in numbers, you would see that really is true.
Right.
Okay. Now, let's go over to this function here. F of, remember this function I asked you about before, f of x equals 8. And you said the derivative of that is also 8. If that was true, what would that mean?
That would mean that well, if we increased x by 8, then the function would increase by 8.
Go back to here. What does this mean?
That means if we increase x by 3.
Actually, the derivative tells you what happens when you increase x by 1.
Okay.
Let's go back to this example. So what does this tell us?
If we increase x by 1, then the function increases by 6.
Remember that we proved that with our little table here, right? Every time we increase x by 1, the function goes up by 6. Notice this doesn't tell us what happens when we increase x by 6. This doesn't mean that if x goes from 0 to 6, the function will increase by 6. You can see that from the table. The table says that when x increases by 1 unit, the function increases by 6. And then when x increases by another unit, the function increases by 6 again. And then when x increases by another unit, the function increases by 6 again. Okay, so how would we interpret this again?
Okay, so if the function increases by 1, if x increases by 1, then the function increases by 6.
Good. And how would we interpret this?
If x increases by 1, the function increases by 3.
Good. So remember, they're doing this example now.
Right.
So if this was the correct derivative, how would we interpret it?
If x increases by 1, then the function increases by 8.
But is that true? Let's make a little table. When x is 0, what's the value of this function? When we input 0 into this function, what's the output?
0?
Think again. Go back to pre-calculates and evaluate this function. What would be the value of this function when x is 0?
I'm not sure. 1, maybe?
You're not sure how to put this into the function? Let's try an example here. So if I put... what would be f of 0 for this function?
It would be 0.
As we put in our table.
Right.
And what would f of 1 be for this function?
6.
And what would f of 2 be?
12.
As we already put in our table here. So the point is the way you use a function is you take your input and you put it into the formula, and then the formula tells you what the output is.
Okay.
So if the input to this function is 0, what would be the output?
0.
Actually, that's not correct. So the thing that's giving us trouble here is, it's like I said earlier, it's actually the easiest cases that give people the most trouble. This formula tells us that when you put in 0 for x, the output is 8.
Okay.
Right? The output is 8. How about if I put in 1 for x? What's the output? 8.
It's still 8.
So I guess what's probably confusing you is it seems like there's no place to actually plug in the x. But that's true, because this is a function whose output is always 8. This is a function whose output is always 8, no matter what the input is. Like I said, sometimes it's the easiest cases that give people the most trouble. If you wanted to, you could make yourself more happy by saying that this was the function. then you'd be able to plug in for x, right? But
Okay.
this is still the same function, right?
Right.
As before. Now, if I plug in x equals 2, what's the value of the function?
It's still 8.
How about if x is 3?
It's also still 8.
Okay. Well, we
Yep.
don't really need this. The point is, this is simply a function who doesn't care what the input is.
Okay.
Another way of putting it is, this is what's called the constant function. And why is it called a constant function? Because it always has the same output. All right, so when we increase x by 1 unit, how much does the output change?
0.
So what should be the derivative?
It should be 0.
Okay. All right, so when I was giving you the problems that involved variable functions, you were correctly figuring those out. But what you might not have remembered from class is the derivative of a constant function. Like I said, sometimes the simplest cases are the hardest. Well, we just actually proved what's the derivative of a constant.
It's 0.
That's right. How did we prove it? By knowing what derivative means. Remember, the derivative tells you how much the function is going to change when you change the input. Well, how much does a constant function change when you change the input? It doesn't change at all. That was what was making us feel so uncomfortable. This doesn't even care what the input is. Okay, so what's the derivative of a constant?
0.
And we just kind of proved that by understanding what derivatives mean. Okay, so how would we interpret this? This means that when we increase x by 1 unit, the function changes by 0, which means it doesn't change at all, and we know that that's really true. Okay. So what would this derivative be?
Is that function of x equals 4?
Sorry, I was trying to write the number 4.
Okay. 4. Oh, okay. It would be 0 still.
That's right. And how would you interpret that?
As x increases, the function does not increase.
Yeah, when we change the input, the output doesn't change at all. What's the derivative of a constant?
0.
That's right. Okay. How about this?
This would also be 0.
And how would you interpret that?
As x increases, the function does not increase.
That's right. Going back to this example here, was this a constant or a variable?
Constant.
How about this?
Variable.
How about this?
Constant.
Good. There was a couple examples on the website like this. What would the derivative be here?
This would also be 0.
Good. And how would you interpret that?
As x increases, the function does not increase.
Yeah, it just stays at pi. This is a function who always outputs pi no matter what the input is. Good. What would be the derivative here?
12 pi to the third.
Now, this time I think I fooled you a little bit. So what you're trying to do here is you're trying to apply the same rule that you applied to this example.
Okay.
But the rule that you were applying there, that applies when this number, is this number a variable or a constant?
That's a variable.
It's a variable. This derivative rule that you applied only applies when you're taking a variable to a power. So you know what to do when the variable is to a power, but is this here a variable or a constant?
That's a constant.
It's just a constant. Okay, so this is why I'm making such a big deal about not confusing variables and constants. So what's the derivative here?
0.
That's right. And what does that mean?
As x increases, the function does not increase.
That's right. And you know it doesn't, because if you it always just keeps giving you 3 pi to the 4th, no matter how you change things. Okay. So notice even if things look kind of similar, they can be different if one expression has a variable and another expression has a constant. Okay, what's the derivative here?
This is 6x. Derivative of 6x.
Good. So what's this for that same problem?
27? No, that's not true. Hold on.
You can use your calculator if you want.
Okay. 6. It's 6x, so 18.
Good. You can use a calculator on your tests, right?
Yep.
Okay, good. Now, what does that mean? So let me help you. I'll tell you what that means. This means that if x starts at 3 and then increases to 4, the function will increase by approximately 18. So that was a little complicated, but this is saying that if x starts at 3 and increases by 1 unit to 4, the function will change by approximately 18. Remember, the derivative usually only tells you the approximate change because it only gives you the exact change when the function is a straight line. When the function is a curve, it only tells you the approximate change. Okay. So how would we interpret this derivative?
If x is at 3 and increases to 4, the increase of the function is approximately 18.
Yeah, the function will increase by about 18. So what's this?
$12.
How would you interpret that?
As x increases from 2 to 3, the value of the function increases by approximately 12.
That's right. Good. So notice that in this case, the derivative is different at different points. It's only when you have a straight line that the derivative is going to be a constant. Normally, the derivative is a function of x. Good. What's this?
6.
Now, careful to notice the symbol that I used here.
Oh, okay. Function of 1. 3.
Good. Now, does that mean that if x starts at 1 and we increase it by 1, the function will change by approximately 3? Well, no, because this is the function, not the derivative, right? So I'm just trying to warn you, don't confuse the function and the derivative. We don't really have an interpretation for the function. It's just the value of the function. It's the derivative that tells you how much the function would change. Does that make any sense?
Yep.
Okay. Okay, let's do this.
Okay. Okay. So f prime of x will be 3x squared minus 6x plus 0, or just left alone.
Good, because what's the derivative of a constant?
0.
Good. So you probably already knew how to do this. Notice that earlier I kind of threw off your intuition because I gave you a function that was just a constant. And then you had some trouble seeing that the derivative is 0. But from doing your practice problems, you might already be comfortable with constants that are part of a larger function. Okay, but in both cases, it's the same idea. The derivative of a constant is 0. Okay, good. So what's this?
F prime of 1 would be -3.
3 minus 6 is minus 3. Good. How would you interpret that?
As the function increases from 1 to 2, as x increases from 1 to 2, the value of the function decreases by 3.
Good. That's good that you took your time and phrased that correctly. As the input increases by 1 unit, the function is decreasing here. Did you say by approximately 3 units? This is not a straight line, so it'll give us the approximate change. Good. And there's also another interpretation. This also tells us that when x is 1, the slope of the tangent line to the function is -3. Those are two valid interpretations. So another interpretation here is that when x is 1, the slope of the tangent line to the function is -3. Okay, good. Okay, let's try this.
Okay. Okay. So f prime of x is 6x squared plus 2x.
Is that it?
Yep.
Okay. I was trying to trick you into saying that the derivative of this is 4.
Right.
But you saw that this is pi is a constant. So we don't apply our normal derivative rules here. There was an example on the website like this. So we have to keep in mind that pi is not the same thing as an x. Okay, so you did that correctly. Good. Do you know how to take this derivative?
One second.
Sure. Yeah, and all of these you should just be working out on a piece of paper, and you can just tell me what you get as you go.
Well, I believe it's 1, but I'm not sure.
How did you work that out?
Square root of x is to the first power, so 1 times the square root of x, and then n minus 1, which is 0, so...
Okay, well, let's work that out together. That one we need to work on some.
Okay.
Okay, so it looks like you've definitely learned how to find derivatives of regular polynomials and constants. So let's move on to something that you looks like you're not quite sure about yet. So the key thing is, what we've been doing here is you already know how to find the derivative of this type of function. It sounds like you've learned that what you do is you take, or this type of function, you take the exponent down and then you reduce the previous exponent by 1. And now we want to learn how can we apply that to a square root. Rather than learning a whole new method for square roots, we want to turn this into a polynomial. So here's the key. So this is 16 to the 1/2 power.
Okay.
Do you know what that means?
16 to the 1/2 would mean.
Do you know what a fractional exponent means?
Not exactly, no.
That means square root of x.
Okay.
Let me give you a couple of examples so you can see the pattern. So 4 to the 1/2 would be square root of 4. Would you agree that these are both valid ways to write square root?
Is that 2 square root of 4?
So, but maybe I'll give you a couple other examples here. So, for example, what would this mean? That means the cube root of 8.
Okay.
And this means the cube root of 9. And this means the 4th root of 8.
Okay.
And this means The fourth root of 10. So this isn't calculus. This is going back to some high school math and learning some ways to deal with square roots or roots in general. Or this is what fractional exponents mean. This is what fractional exponents mean. For example, if I tell you, say, x to the third, what does that really mean?
Well, it means x is going to multiply by itself 3 times.
That's right. It means x times x times x. Or what does x to the fourth mean?
X times x times x times x.
That's right. That's something you might remember from high school, but what you might not have learned to remember from high school is what fractional exponents mean. They don't seem to fit into this pattern. Well, fractional exponents are roots. Fractional exponents are roots. Let's actually review roots a little bit here. So, what does this simplify to?
4.
Why? How do you know?
Because 4 times 4 is 16.
That's right. That's what square root means. The square root is kind of difficult to put into words. The square root of 16 is the number that if you multiply it by itself, it gives you 16. It's kind of hard to put it into words, but 4 is the square root of 16 because 4 squared is 16.
Right.
And what's this?
5.
How do you know?
Because 5 times 5 is 25.
Right. But do you know what a cube root is? What's the cube root of 8?
2.
That's right. How do you know?
2 times 2 times 2 is 8.
That's right. Because 2 cubed is 8. Okay. And maybe I can try one more example. Do you know what the fourth root of 16 is?
It would be 2.
That's right. How would you check that?
2 to the 4th equals 16.
That's right. Okay. So now we understand what those roots are. But it turns out that roots can always be written as fractional exponents. For example, square root of 16 could also be written as 16 to the 1/2 power. So how could you write square root of 25 with a fractional exponent?
25 to the 1/2 power.
And how would you write the cube root of 8?
8 to the 8 to the 3rd.
8 to the 1/3.
To 1/3, okay.
Yeah. Because 8 to the 3rd would be 8 times 8 times 8, which is a huge number, not 2.
Okay.
What would this be as a fractional exponent?
16 to the 1/4.
That's right. Not 16 to the 4th, because that would be a huge number, not the number 2. By the way, notice that when we talk about a cube root, we have to put the number 3 over here to show that it's a cube root. And when we talk about a fourth root, we have to put the number 4 in this little pocket here to show it's a fourth root. When you talk about square roots, you could put the number 2 here, but people usually leave it out and it's just assumed it's a square root. If no number is written in this little pocket, it's assumed that you're talking about a square root. But it might help to put the number 2 here so you can see where the denominator from this fraction is coming.
Okay.
So what does this mean? What's another way to write this?
3 square root of x.
3 square root of x, like this. So no, what I was going for is this is the cube root of x. Like this. Maybe that's what you were thinking of. Maybe that's actually what you were thinking of. Yeah, it might just be hard to put into words. So this is called the third root of x, or the cube root of x. And this is read the fourth root of 16. So this is the cube root of x, or the third root of x. How would you rewrite this?
The fourth root of x.
Good. How could we rewrite this as an exponent?
X to the 1/5.
Okay. So let's look at the example we were working on earlier. We want to take the derivative of this function. Well, we haven't learned any rules for taking derivatives of square roots, but we have learned rules for taking derivatives of polynomials.
Okay.
So how could I rewrite this as with an exponent?
Write it as x to the 1/2.
That's right. Now we can take the derivative. You'll have to be careful to follow the rules exactly correctly. So what would be the derivative of this, do you think?
It would
if
be,
we follow the previous pattern.
Would be 1/2 x to the negative 1/2.
There you go. Okay, good. 1/2 x to the negative 1/2. All right. So the reason we had to do this digression about fractional exponents is because we need that so that we can keep taking these derivatives of square roots. Okay, good. Okay, and there's certainly a bunch of problems like this in the web, on the web problems. So this is important for your course. All right, so now that was the problem I think that was stumping us before. Before I was asking you what the square root of x was. I think we just had a guess that that was 1, but we can see now that that's incorrect. Instead, we've worked that out down below now. So let's try this one. What would this be?
This would be x to the 1/3.
That's the derivative?
Oh, okay, sorry. So we'd have f prime of x as 1/3 x to the negative 2/3.
So x to the 1/3, that's not the derivative, that's another way to write the function. And then following the rule, we take the exponent down, and then it looks like you were careful to do 1/3 minus 1, which is minus 2/3. Okay, so notice that the first step, rewriting the fractional exponent, that didn't give us the derivative, it was just another way to write the original function. And only then were we able to find the derivative. Okay, try this example.
Okay, so we'd have f prime of x equals 1/4 x to the negative 3/4.
Good. So I can't see what you wrote there, but you probably did something like this. You took the x, and you said that the original function can be rewritten like this, and then you can use our normal derivative rules to go from the function down to here. All right, that looks good. So in this example, figure out what f prime of 2 is.
Okay, so I guess I could use a calculator here, but yeah, let me
go ahead and use your calculator.
Okay, 1 second. Okay, so would it be okay to give this answer, I guess, in decimal form?
Or that sounds good to me.
Okay. Okay, so we have f prime of x equals negative 0.375 to the negative 1.75.
To a power?
Right.
I'm not sure how you got that on your calculator. All right, but in any case, so yeah, I thought we might have some trouble with this on the calculator, so let me take you through that. So here we have this. So so here's how we should do this. We start with 1/4 times what?
2.
Now I have to raise to a power, right?
Okay.
Oh, I don't know. So does what type of calculator do you have?
I have a TI. It's an 83 plus. Yeah.
Yeah.
Yep.
Do you have
83
a
plus.
so the new versions of those calculators, I think, give you templates like this. Do you have a calculator that does like exponent templates, or does everything stay on the same line on your calculator?
It stays on the same line.
Okay. So I should have.
But I think what I did was I plugged in 2 for x, and I multiply that out by 1/4. I think at 0.5, and I found the. I think I found the. No, that's not what I did. I'm not sure what I did.
All right. One moment.
Yeah, I found f prime of. I don't know.
There we go. Okay, so I'm just going to demonstrate the right way to do this on the calculator. So take a look at how I've done this. Do you see the rationale behind plugging it in like this?
Yep.
Okay, so I can't see what you did, so I'm not sure exactly what the problem was the first time when you were using your calculator. But anyway, this is the correct way to enter it in. Since you have an old calculator that doesn't do templates, you have to put parentheses here to tell it that this whole thing is the exponent. There's no parenthesis where we wrote it out, but I have to put a parenthesis to show this whole thing here is an exponent. Okay, so try that on your calculator and see if you get the same answer.
Okay. I get 0.14865.
Okay, good. So we'll call that 0.15 to summarize. Okay, all right. So so this is important. There's a few different problems in your in the sample problems on the website that are like this. Usually on the website, your instructor doesn't ask you for f prime of x. They ask you for the derivative of a particular number. So we need to be able to plug this into the calculator. Okay, so we spent a little time on this now, but now we've seen how to do this on the calculator. Does that make sense?
Yep.
All right. Well then. So let's try this.
Okay. X to the 1/2.
Oh, yeah. That's right. Good. What I meant to say was this. Oh, actually, actually your answer was incorrect there. So maybe we should go back to that. So what's the answer to this question?
X to the 1/2.
Now, I think you got confused there. This is the derivative, but you just told me another way to write the original function. Remember, x to the 1/2 is not the derivative. It's just another way to rewrite the original function. We haven't actually taken the derivative yet.
Okay, so now f prime of x is 1/2 x to the negative 1/2.
That's right. Okay, good. So we don't want to confuse these two steps. When we rewrite this with the fractional exponent, that's not taking the derivative, that's just rewriting the function in a form that's more convenient to us. So one thing that's important is that when you're writing these things out, you have to use good labels. So something that people oftentimes do that's bad is to do this problem, a lot of people would just write this. And then maybe this. That's very bad because these have no labels now.
Okay.
Anytime we write something down, we have to give it a label. What's the label for this?
That is f of x, and the one on the bottom is f prime of x.
That's right. So I can't see what you've been writing down. To save time, I've been just having you talk me through this so we don't have to keep going back and forth between your screen and mine. But anyway, you want to avoid just writing things by themselves. You always have to write each expression down with a label so that we know what it actually stands for. Okay. Good. So let's now try this.
Okay. All right, I plug that in my calculator and I get 0.28867.
Good. So I'll approximate that as 0.29. Excuse me. Now again, we should not write this. Instead, we have to write it with the label. We want to try and get in the habit of writing equations and not just expressions or numbers by themselves. So let's try this problem.
Okay, 1 second. $1.6.
1.6?
Yep. 4 to the 1/3.
Okay, did you give that a label?
F prime of 4 equals 1/6, and right above that I had function of x equals x to the 1/3.
So you wrote x to the 1/3. And what was the label you gave this?
Function of x, so f of x, and then below that had f prime of 4 equals 4 to the 1/3, and then I solved for that in my calculator.
Okay. Now, tell me what was the label for this?
That was f of x.
Good. Now, how did you calculate f prime of 4? What did you do?
I plugged 4 into... okay. Now I see what I did wrong. But yeah, I plugged 4 into my function.
Right. You plugged 4 into your f, right?
Right.
But what should we be plugging it into? We should be plugging it into the f prime. So this is another good example, again, of why we need these labels. But of course, we need to write down the labels, and then we need to use them. So you correctly saw that this was the function, but then we're not ready to figure out the derivative yet. Okay, well, try again. What do we do instead?
Okay, so we have to rewrite f prime of x as 1/3 x to the negative 2/3, and then below that we can write f prime of 4.
So we have 1/3 x to the negative 2/3, and what's the label for this?
Function of x. Sorry, that's incorrect. This would be the f prime of x.
Okay, good. Okay, and then
below that,
next result is.
We can... So we get f prime of 4 as 0.13.
0.13, that's what I got. And you labeled that as f prime of 4. Okay. Okay, so let's pause here and see what's the problem that's messing us up here. I think one of the most common mistakes that people make in calculus is they confuse the function and its derivative. And that's what's messing us up here, confusing the function and the derivative. What's the symbol for the function?
Function is f of x, right.
And what's the symbol for the
Okay.
derivative?
F prime.
F prime. So a lot of people aren't careful enough to treat those two things separately here. So we have to be very careful to separate them from each other. So what does this stand for?
Function of x.
And what does this stand for?
F prime of x.
What does that stand for?
That's derivative.
The derivative of the function.
X. A function.
What does this stand for?
That stands for the function at 2.
Yeah, the function at 2. And what does this stand for?
That's derivative at 2?
Yeah, that's the derivative at 2. So what went wrong in this problem? What went wrong was I asked you for f prime of 4, and what you told me actually was f of 4.
Okay.
So what you gave was kind of correct. It was a correct answer, but just to a different question. Remember that your original answer was 1.6, I think, and that is a correct answer, but it's an answer to a different question. If I'd asked you what f of 4 was, the answer would be 1.6, but instead we were asking of f prime. So the key is make sure we don't confuse the function and the derivative, and label each step so that you know which is the function and which is the derivative, and make sure you're answering the right question. Sometimes the question will ask you for a function, sometimes the question will ask you for a derivative. All right? Okay, so we need to make sure we can get these right. So let's try this example. Take your time and work that out on paper. Try to use the techniques we've been talking about.
Okay, so for the first line, I wrote function. Well, I rewrote the problem anyway. And then for the first line below that, I wrote the f prime of x equals 1/4 x, then negative 3/4. And then below that, I wrote the f prime of 5 equals 1/4 times 5 to the negative 3/4.
Good.
And now I'll solve that in my calculator. And my answer comes out to be the f prime of 5 equals 0.075.
Okay, you did that correctly. That was good. Try this problem. Oh, I didn't give you a question. So here's the question.
Okay, so first line I wrote f prime of x equals x to the negative 1/5. And then below that I wrote f prime of 3 equals 3 to the negative 1/5. And now I'll solve that with the calculator.
Okay, let's back up. I'm not sure where you got this line from.
That line I got from rewriting. Wow. I just made the same mistake I made.
So take your time.
Okay.
Slow down and take your time. It takes a little while to get the hang of it, but we want to make sure we have this down before we move on. So take your time and work out the steps. This is an important type of derivative in the class.
Okay. Okay, so we have the function, so we need to write what f prime is, and f prime equals f prime is... Huh, I think I messed up again. Alright, I have negative 1/5 x to negative 6/5 as f prime of x.
Okay, so I think you might be getting a little confused here, so let's make sure we have this right. So here's the question. What's the next thing you wrote down? What's the first thing you wrote down to solve this problem?
I rewrote the root as x to the negative 1/5.
Where are you getting that negative sign from?
Oh, okay, I thought... Okay, sorry, I misread the problem, I guess. Okay, so it should be x to the 1/5.
Okay, yeah, maybe, I don't know, maybe the way I wrote it wasn't clear. Okay, so yeah, so you have x to the 1/5?
Yep.
Okay.
And now
what's that labeled as?
This is f prime of x. No, sorry, that's f of x. Yeah, it's f of x. Okay. So I'm just going to rework f prime now. I think I'm stuck.
Okay.
Yeah, I'm stuck. So I have f of x as x to the 1/5,
Okay.
and then I'm not sure where to go from there.
Okay, well,
I know f prime of x should be 1/5 x to the negative 4/5, but when I try and solve for that, I get an error in my calculator.
oh, okay. Maybe I screwed you up then. Let's see here. Does this not work? No, this should work fine. Okay. So you got f prime was 1/5 x to the negative 4/5. Okay. All right. So here's my calculator. So tell me, what are you typing on your calculator to do that?
1 divided by 5 times 3 to the negative 4/5.
Did you put that in parentheses?
Yeah, I put the exponent in parentheses. So parentheses negative 4.
I don't see why that should give us an error.
No, I don't get... yeah, I guess I did something different. But now my answer is 0.083.
Okay. All right. You might want to. So your calculator should show you what you did previously, so you should be able to see how that's different from this.
Okay, I cleared it out.
Okay.
I guess I should have
All right.
done that.
All right. Well, in any case, so it looks like now we're both getting the same answer, 0.083. And what's the label for that?
That's f prime of 3.
Okay.
Derivative prime 3.
Okay. All right. So here's our technique for that problem. Do you have that in your notes now?
Yep.
All right.
I just need to be careful. This is obviously very easy to trick me up here.
All All right, let's switch. I'd like to watch you do this now. So let's shift to your screen. So copy this problem down onto your piece of paper, and then make sure you copy it accurately. And then when you're ready, see if you can turn your screen sharing on.
Okay.
So now try working out that problem. And take your time. We need to just make sure we can get one of these right before we move on to the next topic. So take your time and try to apply the techniques we've been talking about.
Okay.
Okay, that looks like a good systematic approach. You wrote out each step, and the important thing is that you labeled each step as you went. All right, now, so notice that one thing that we've been learning here, we went back to some high school math that some people might have forgotten, and we saw what fractional exponents meant. Something else some people have forgotten is what negative exponents mean. Do you know what x to the negative 3 means?
I don't know.
So that means this. Okay. That's just a way that negative exponents are defined. So x to the negative 3 really means this. So take a guess. What do you think x to the negative 4 means?
1 over x to the 4th.
That is correct. How about x to the negative 7?
1 over x's 7th power.
That is correct. How about this?
1 over x to the 1/3.
That's right. Good. So the technique we want here is, remember that in order to take derivatives, we need to write things in as being raised to an ordinary power. We need to get rid of the root symbol and just show things being raised to a power. Let's see how we would do that here. So let me give you an example. So 1 over the square root of x. Well, square root of x really means x to what power?
1.
Take your time. What does the square root of x really mean? That's x to what power?
Oh, square root of, okay. Square root of x is equal to x to the 1/2.
That's right. Does that make sense so far?
Yep.
Now, how could you rewrite this then as just x to a power?
X to the negative 2?
Let's see. Actually, no. Let me give you a couple warm-ups for that. How would you write this as x to a power?
X to the negative 5th?
That's right. How would you write this as x to a power?
X to the negative 7. Okay.
Good. So how would you rewrite this as x to a power?
X to the negative 1/2.
That's right. I think the first time we were maybe changing the 1/2 to something else, but all we have to do is stick in this negative sign. Okay, good. Do you see the advantage of this? The advantage is now you know how to take the derivative of this, whereas you didn't know how to take the derivative of the original. Let's say that you had, say, 1 over the cube root of x. Now we can't take the derivative of that, so we need to rewrite it as x to an ordinary power. Well, it's a two-step process. First of all, this could be 1 over x to, 1 over x to the what?
1/3.
That's right. And now how could I rewrite that as just x to a power?
X to the negative 1/3.
Yeah, not x to the negative 3, x to the negative 1/3. Okay, no, so that is the technique. And the advantage is that we don't know how to take the derivative of this expression, but we do know how to take the derivative of this expression. Okay. Okay, so here's a sample problem. Maybe we'll try working more on your screen now. Can you turn on your screen sharing? Copy this problem down first, and after you've copied it down onto your paper, see if you can turn on your screen sharing. Now our goal here is to rewrite that as something that's easier to take the derivative of. Okay, seems like that worked out fine. Good. So I'll go back to my screen for a moment, but you did that correctly.
Okay.
Okay, copy this problem onto your paper, and then we can move to your screen, and you can show me how you would do that.
Sorry, that's a little sloppy there, but yeah, I have f prime of x equals negative 1/5 x to the negative 6/5.
Good. So that's right. You have to be careful. You're doing negative 1/5 minus 1. And negative 1/5 minus 1 is negative 6/5. Good.
Right.
So that came out correctly. So it looks like you were careful with that and you did that correctly. Now for this same problem, and we do want to try to be as neat as possible because as in math, otherwise it's easy to make mistakes. So for the same problem, now let's add on to that same problem and let's figure out f prime of 2. So you can write down now that the next part of that same problem is to find f prime of 2. There you go.
Okay.
Okay, good. That was a good method. We were careful there, and we didn't make any careless mistakes. Good. I'm going to go back to my screen for a moment.
Okay.
Okay, copy this onto your paper, and then we'll shift to your screen, and you can try this problem.
Okay. I should. I'm just gonna.
Did you copy down the question was? It was.
Yeah. I'm just gonna put this up here.
Good.
Negative 1/3 minus 1. Okay. Okay.
Okay, that looks like a good, careful approach. We avoided careless mistakes. You took the derivative correctly. You said negative 1/3 minus 1 is negative 4/3. So that was a good, careful way to work out that derivative. Okay, so now, I think on your own, you had already learned how to find derivatives of normal powers. But something else that was covered is how to take derivatives of roots. So now we've covered that. And notice now we have some pretty powerful techniques. We can find the derivative of a root even if it's in the denominator. Now we know how to get the root out of the denominator as well. So notice our basic technique here when we see something weird is to try to rewrite it as a normal power of x. So we can use our normal formula for finding derivatives. Okay, now you did that correctly. So let me ask you, how would you interpret your answer? Do you remember we worked on interpreting this? Do you remember what's a way to interpret this?
So as x increases from 2 to 3, the value of the function increases by approximately, well, it decreases by negative 0.1323.
Approximately.
Approximately.
Okay, good. That was good. Okay, so that's a complicated idea. But I think you were on the right track for articulating that. Okay, good. So that's the correct interpretation. Okay, here's another problem. So let's follow the same pattern. Try copying this onto your paper, and then we'll shift to your screen, and you can try working it out. Good.
Okay. Hopefully that's correct.
Let's see. Try that on your calculator one more time. Nope, don't bother. You were right and I was wrong. Okay, good. Yeah, you got that correct. Good. Of course, if this was a test question, it would be worth it to do everything twice on the calculator because it's easy to make an entry mistake. But actually, it was me that made the mistake. Okay, good. So one of the most important things you did here is that you took your time. There was a couple points here where you had a little difficulty and a little uncertainty, but the important thing is you didn't just take a guess and hope for the best. You took your time and thought about it, and you wrote down the right thing. So our goal here is not to be speed demons, but to make sure we have a reliable approach. And you took your time and you used a reliable approach. So that's good. So how would you interpret your answer?
As the value of x increases from 2 to 3, the value of the function increases by 11.65. That's approximately 11.65. Not exactly.
Yeah, it'll increase by approximately 11.65. Or, to use your calculator, it would increase by approximately 11.646444661. Okay, good. The derivative only gives us the approximate change. Okay, good. So now I just gave you a more complicated example where the root was in the same function with some other powers, but you adapted to that, and you saw the correct way to attack that. That's good. I'll go back to my screen.
Okay.
Okay, good. So we've made some good progress on evaluating those square roots. So here's another function.
Okay.
Do you remember this from your class? Do you know what the derivative of this function is?
Yep, he stated that we'd prove this later. The same with the constant as well, which is why I think I had trouble. But I think he said that this derivative is just itself, so it would be e to the x.
Like this?
Right.
Okay, that's good. That is correct. Now, I don't think we have to worry too much about the proofs. I'm pretty sure you're not going to be tested on any proofs. The important thing here is to learn the rules. And it looks like you've got that rule down. So this is a pretty easy derivative to take. That's good. What's this derivative?
4x to the third.
Good. But it seems like you followed a different pattern over here. You didn't say that this was... It seems like if we were following the same pattern, we might say that the derivative was this. Do you see how I got this? Mm-hmm. Now, this is a mistake. This is wrong. Do you see why this pattern doesn't apply to this function? You can use some of the concepts we've talked about earlier. Why does this pattern not apply to the function e to the x? How can you see that they're different?
Because the power is a variable and not a constant.
That's a good answer. Yeah, that's a good answer. We can be more specific here. So in this case, so the terminology here is, here x is called the base and 4 is called the power. And here e is the base and x is the power. So in this case, is the base a variable or a constant?
The base is a variable.
And how about the power?
Constant.
So this rule that we used here only applies when a variable is raised to a constant. Well, how about in this example? Is the power a variable or a constant? Is the power a variable or a constant?
The power is a variable.
X. And how about e? Do you know, does e stand for a variable or a constant?
I'm going to assume it's a constant because it's at the beginning of the alphabet.
That's right. E is like pi.
Okay.
It just stands for a number. Do you know what number pi stands for?
3.14?
Yeah, 3.14 approximately.
Right.
Good. And e is just a number too. Do you have any idea what number e is?
This is bad. I mean, I've used it in like Gen Chem and stuff, but I forget 10. Like I want to say it's base 10 something, but I could be totally off.
Yeah, is that something a little different? Well, let's go to so on your calculator, do you have a little e symbol above the divide key?
Yep.
Good. So you should be able to hit second
E.
And then equals. And what do you get?
2.71.
So that's what e is. Okay.
Okay.
Okay, so that's a new number that's important. When you were in high school, I think there was probably a lot of times when pi was an important number, but now in your calculus course, pi will still be important, but e will also sometimes be important. So what should I write down for e? E is approximately
2.72.
2.72, and notice that there's a key for that on your calculator. So if you ever need to know what e is, it's right above your divide key. Notice there's also a key on your calculator for pi, right above the power key. So if we forget, if we need a value for either of those, the calculator would always tell us. Okay, good. So going back to here, the example that we were looking at, in this case, is the base a variable or a constant?
The base is a constant.
And the power?
Variable.
And that's why the rule that we used for this derivative doesn't apply over here. So the rule where you take the exponent down and then you subtract 1 from the previous exponent, that only applies when the base is a variable and the power is a constant. It doesn't apply at all if the base is a constant or if the power is a variable. So that's why we can't use that old rule over here. So this, what I wrote down here, would be a wrong approach. That would be applying a pattern where it doesn't apply. So it would be wrong to apply that. I'll erase that since that was wrong. Instead, the correct answer is, in this particular case, the derivative is just e to the x. This doesn't mean that whenever you have a constant to a power, that the derivative is always the same as the function. That only happens for e. So you might wonder why the heck do we care about this weird number 2.72? Well, what's cool about 2.72? Well, one cool thing is that 2.72 to the x is its own derivative. So we can already see why we're interested in this number, because most numbers don't work that way. Okay, it wouldn't work that way for pi, say. Okay, good. All right, so let's see. All right, what do you think is the answer to this question?
Three e to the x.
Okay, good. Because the derivative of the of this exponential function is just the same thing that it started with. Good.
Okay.
So you got that correct. Good. Do you know how to figure this out for the same problem?
It would be 3 e to the 4th. Oh, well, no, that would be a con. I think it would be 0.
Why 0?
Because e is a constant, 3 is a constant, and even though you're plugging in a variable into the power, I don't know if that logic makes sense or not, but...
All right, I think you might be confusing this with something that we said earlier. So what we said earlier is that if a function... So, do you know what this is? Maybe I'll make this easier. Do you know what this is?
0?
Because the derivative of a constant is 0.
Okay.
So what's this for the same problem?
It's still 0.
Still 0. That's right. I think you might be thinking of this idea.
Right.
But this idea doesn't apply because this only applied here. How did we know this was a constant? Because everything in the function was a constant. A constant raised to a constant power is a constant. But here we have a constant raised to a variable power. So is this function always going to give you the same output? Well, no, because e to the 1 is not the same thing as e to the 2, which is not the same thing as e to the 3, which is not the same thing as e to the 4. If you plug in 3 for x, you'd have e to the 3. But if you plug in 5 for x, you'd have e to the 5. So this is, so notice a function is not a constant just because there's a couple of constants hanging around in it. A function is only a constant if it only involves constants, generally speaking. So this is a variable function, even though some of the things in it are constants. So there's really a pretty straightforward way to evaluate this. Now that we know that f prime of x is 3 times e to the x, how would you figure out f prime of 4?
3 e to the 4th.
That's right. Good.
And then
so we should just use our normal method of plugging in. All right, good. So go ahead and work that out on your calculator.
Okay. I get 163.8. F prime of 4 equals 163.8.
Okay, good. Now, actually, depending on the situation, you might just leave the answer like this, 3e to the 4th. Sometimes the instructor doesn't require us to simplify our work. So we could say it's 163.8, or we could actually plug in and get this, 3e to the 4th, I mean. So how did you do that on your calculator? Did you do it like this? 3 times e, like so?
Yeah, basically, I just typed in 3 second e raised to the 4th, but yeah,
that's right.
Thing.
So you actually don't need the times here. Good. I just wanted to point out, you could also do it like this. There's another e button on your calculator I just wanted to point out. You have this natural log button here.
Okay.
Notice that if you do second, you get another e. they're pretty much the same thing, except this e automatically raises itself to a power, if you see what I'm saying. So actually, they turn out to be pretty much the same thing. It's really just a matter of taste. So you can use either one, and hopefully I'll get the same answer. Yeah, I did. Okay, good. Okay. So try this problem. Copy it onto your paper, and then you can do it on your screen.
Well, this is... Anyways, I'll just keep going. Okay. Okay.
Check that on your calculator.
Okay, so e to 0 is 1. All right, so...
Okay, good.
Okay.
So when we raise, what is anything raised to the 0th power?
1.
1, not 0. That might seem a little surprising, but it turns out that anything to the 0th power is defined as 1. So it looks like on this problem I gave you some simpler numbers, so we tried to do it without a calculator. That's fine, but the calculator is a good backup in this case because sometimes people get confused about that 0 exponent. Okay, good. So we got that f prime of 0 here is 4. Okay, so that came out to be correct answer. Good. I'll go back to my screen.
Okay.
So what's this?
X. Or, sorry. Well, no, 1.
Yeah,
Okay.
1. And what's this?
1.
And what's this?
1.
Good. What's this?
X.
Yeah, this is x, but this is 1. Good. And what's this?
X to the 1/2.
Like this?
Okay, I'm mixing myself up now. Let me get back. x to the negative 1. Yeah, that's not correct. 1 over x. That's what I would do. 1 over x.
Good. What's this?
1 over x to the 4th.
Good. Not x to the 1/4.
Right.
And what's this?
1 over x to the 5th.
So actually, I think this is what you did. The first thing to say is that this is 1 over x to the 1. But how can I simplify the bottom now?
Just 1 over x.
Yeah, that's right. This is another good example of how, for some reason, it's the simplest cases that give people the most trouble in math. I think if I'd given you these problems, we wouldn't have had much trouble with it, but the simplest example is the one that throws off people's intuition. Okay, so this is all some algebra skills that are important for the material that we've been going over. Good. Okay, make sure you copy this problem carefully and then show me how you would do it on your screen.
Okay. Okay.
Okay, excellent. I was trying to trick you here, but you didn't fall into the trap. So the point here is, remember that the biggest problem we've had today, or one of the biggest, is making sure we don't confuse the function and the derivative. So I wanted to make sure that you were paying close attention that in this problem, it was asking for the function, not the derivative. So we didn't actually have to calculate any derivatives in this case.
Okay.
And you did that correctly. Good. How would you interpret this? Well, there isn't any fancy interpretation to it. It's just straightforward. When the input of the function is 3, the output is 45. There's no fancy interpretation of this. I guess we might as well finish off by also doing f prime of 3 for the same problem.
Okay. Okay.
Excellent. Good. So how would you interpret that?
As x moves from 3 to 4, the function is approximately, well, the function approximately increases by 30.
Okay, good. So what is f of x here?
F of x is 5x squared.
Excellent. What is f prime of x?
10x.
Good. What is f of 3?
F of 3 is 45.
Good. And what's f prime of 3?
30.
So notice those are 4 different things. Oftentimes
Right.
people confuse those. It's important to realize that those 4 questions I asked you, those are all 4 easy questions, but it would be easy to blow it if you confuse them with each other. So those are 4 different things. We don't want to confuse f of x and f prime of x, or f of 3 and f prime of 3. Those are all different things, and it's important not to confuse them. So is f prime of x the same thing as f of x?
No.
No. And was f of 3 the same thing as f prime of 3?
Nope.
No. Is a function the same thing as its derivative?
Not usually.
Not usually. Good. Now, remember, there actually is one exception. There is one function which is the same as its derivative. That's the e to the x function, right? The e to the x function is weird because it is the same as its derivative. But that's weird. That's one of the reasons why e is an interesting number. We can see that normal functions like this are totally different than their derivative. F of 3 is 45, but f prime of 3 is not 45, it's 30. Write down a function. Well, let's start with the simple function. Go ahead and write down f of x equals 5x squared. And now let's figure out f prime of 2.
Okay.
Good. Now, how would you interpret that answer?
As x increases from 2 to 3, the function increases by about 20.
Good. Good. Or if the function starts at 2 and then increases by 1 unit, it'll increase by about 20. Good. Let's say that we start at 2 and we decrease by a unit. About how much will the function change?
It will decrease by about 20.
That's right. So notice this tells us approximately, if it tells us approximately how much will change if we increase, it should also tell us approximately how much we change if we decrease the input. It won't be exact, but it'll be approximate. Let's say that we start at 2 and then we increase x by 2 units. About how much will the function change?
By about 40.
That's right. How about we start at 2 and we increase the function by about 3 units? How much will the function change?
About 60.
That's right. Good. So notice that even though it only tells us directly how much the function changes when you change the input by 1 unit, it also would let you approximate how much the function would change if you change by any amount of units. However, the approximation will be the best the smaller the change is. The smaller the change is, the better the approximation will be. Suppose we start at x equals 2 and we increase the function by about half a unit. How much do you think the function would change?
It'll be, I guess, about 10, but it's actually more accurate than 20.
Good. Yeah, so it would increase by about 10, and we would expect that approximation to be even better than if you're increasing by 1. Okay, good. Now there's also a graphical interpretation of that number. What's the graphical interpretation?
As x increases to the right 1 unit, y increases by 20.
About 20. Good. Now, that's pretty similar to what we were just talking about. So what I was going for instead with the graphical interpretation is that, yeah. So how would you phrase that?
The slope is 20 as x moves from 2 to 3, the slope is 20.
Or we could just say, now the slope of who?
The slope of the function.
That's true. That's but it's not quite clear what we mean by the slope of a function because it's not a straight line. So a more clear interpretation is that when at x equals 2, the slope of the tangent line to the function is 20. When x equals 2, the slope of the tangent line to the function is 20. Okay. Okay, good. All right, so those are all important interpretations to keep in mind as we're going. So let's write down another function. Let's write f of x equals 6.
Okay.
And let's figure out f prime of 3. Okay, good. So what would be f prime of x?
F prime of x would be 0, 0.
That's right. For any x. So
Right,
that includes
right.
f prime of 3. Good. How would you interpret that answer?
As x increases by one unit, the slope does not change.
Now that interpretation turns out not quite to be right. We're mixing up a couple of the different interpretations. You're mixing up the two interpretations there. So one interpretation is that as x increases by 1 unit, the function does not change. Not that the slope doesn't change, but the function doesn't change.
Okay.
And the other interpretation is that the slope of the tangent line is 0. Those are two different interpretations. So let's try that again. How would we interpret this?
As x increases by one, the function does not increase.
That's right. And you know that's true, right? Because what is f of 1? What is f of 1?
0.
No. What is f of 1?
F of 1. Oh, it's 6.
And what's f of 2?
F of 2 is also 6.
And what's f of a million?
It's also 6.
So the point is, it's true that as x increases by 1 unit, the function doesn't change. Good. So that derivative is one that should already make sense to you. When I asked you what f of 1 was, why did you say 0? Because you were confusing f and f prime, right? Remember, we've talked about how it's really important not to confuse f and f prime. Those are two different functions. Okay, good. So it shouldn't surprise us that the derivative of a constant function is 0, because we can see that a constant function doesn't change. That's why it's called a constant function. Okay. So that's another one that's important for us to know about. So let's try then f of x equals cube root of x. And let's try to find f prime of 2. Okay, excellent. Good. How would you interpret that answer?
As x increases from 2 to 3, or just, I guess, 1 unit, the function increases by 0.21.
Good. That's a good interpretation. And what would be our graphical interpretation?
Graphical interpretation would be the function of x2 has a slope of 0.21.
That's true. However, instead of talking about the slope of the function, there's a more concrete interpretation, because it's not quite clear what slope of a function means.
Okay. The slope of the tangent line.
To the function at x equals 2 is 0.21. Right. That's right. Let me maybe show you what I mean by that. So I think I'll go back to my screen now. So let's see. What was the function that we were just doing? Cube root of x?
Yep.
All right. So let's see. Here is cube root function. And then I can try graphing that. Okay, so I can see, and then I might want to go to where we were doing x equals 2. Oops. So I'll go to trace and x equals 2. So that puts me here on the function. So then I could go over here and graph that. Whoops. So it looks like the graph of that function looks kind of like this. And then if I go, say here, to x equals 2, this would be the tangent line. And what is the slope of this line?
It's very small. It was 0.21.
Good. And you can see from the graph that this is very shallow at this point. It is very shallow with a low slope. Okay, so I think it's important to be able to interpret these derivatives. I know that on the mastery test, that's not going to be what they're focusing on testing. They're just going to focus on the mechanics. But when you get back then to the regular exams, and as we continue with the course, it's important. So basically, after the main thing you're focusing on this chapter is mechanics of derivatives. But as the class goes on, you're going to have to be able to interpret derivatives for word problems. So we'll be best off if we know in the back of our mind what derivatives mean all along. Okay, so this is what I mean by the graphical interpretation. This is what I mean when I say that the slope of the tangent line at x equals 2 is 0.21. Why do we have to keep saying at x equals 2? Because if you went to a different point, there would be a different tangent line, right? For example, if we went to say this point here, the tangent line is much steeper. So that might be the derivative, say, that might be f prime of 0.1, say, right? So if you found f prime of 0.1, that would find the slope of the tangent line when x is 0.1, which would be much steeper. But if you find f prime of 2, that's the slope of the tangent line here. Also, do you see that how the tangent line is an approximation to the function? Notice that right here, the tangent line is very close to the function. So if we increase x, say, from 2 to 3 by 1 unit, where the tangent line is very close to where the function is going to be. That's why the derivative tells you approximately how much the function is going to change if you change the input. It doesn't tell you exactly because the tangent line is not exactly the same as the function, but the tangent line is close to the function, so it gives us the approximate change. On the other hand, notice that if we changed x by, say, 5 units, all the way out to here, then the approximation is not so good anymore. Now the tangent line is not so close to the function. Okay, so it's important to have in the back of our mind as we're doing these mechanical problems what the derivative actually means. Does this example make any sense here? Yeah. So this is actually a good exercise to go through when you're doing the practice problems. It's oftentimes good to, you can use the nice thing about having a graphing calculator is it doesn't take a very long time to graph a function. You can graph the function, then graph the tangent line, and double check that the slope seems approximately right, and that way you're just building your intuition for what derivatives mean. That's not crucial for the upcoming test, but in the later chapters of the course, it's going to be really crucial to actually know what derivatives mean, not just to be able to calculate them. Okay, so let's see, we just did that. So now let's try, let's go back to your screen and let's try finding finding this. We'll try finding f prime of x here.
Oh. Okay. X to the minus 1/2 minus 1. Okay, good.
Done?
Yeah.
Okay, good. So it's good that you went back and double-checked your exponent there. So that's a good approach. By the way, if this was an answer to a test problem, you'd probably want to leave out that caret, because you're putting that in because you do that on a calculator, right?
Right.
But if this was the answer to a test question, we don't usually use carets for exponents. We just put something up in the exponent. Or I don't know, maybe your instructor wouldn't care about that anyway. Of course, if you're planning to go ahead and plug that into a calculator, the caret can be a helpful reminder of how to do that. Okay. So now I'd also like you to figure out, so let's figure out f of 1. Let's figure out f of 1 for that same problem.
Okay.
Good. All right. So I was trying to trick you here. I was trying to get you to do f prime of 1, but you avoided the trick and you actually answered the question that I asked you. Good. So the point of that little exercise was just to hammer home the idea that there's a big difference between f and f prime, and we need to focus on what it is we're focusing on. You ended up maybe overcomplicating this a little because you notice that you've written down 3 different forms of f of x. First, you started by f of x is 1 over square root of x. Then you wrote f of x is 1 over x to the 1/2 power. And then you wrote f of x is x to the negative 1/2 power. And those were all useful steps for finding the derivative. But which of those is the most useful for just calculating f of 1? Well, to calculate f of 1, you may as well have gone back to the original function, right? 1 over square root of x. That's what you ended up with anyway. What is the square root of 1?
1.
So what's 1 over the square root of 1?
1.
Yeah,
okay.
that is what you ended up with, but you kind of ended up retracing your steps. So for this problem, it would have been easier to plug into the very first function of f. That's what you ended up doing, but you could have gone to that directly. All right, but anyway, you gave a correct answer for that. Okay, good. Let's see, 1 second. All right, now let's write f of x equals pi to the 3rd power. F of x equals pi to the 3rd power. And let's figure out f prime of x.
Constant raised to a variable. Okay.
Okay, excellent. Good. So I was trying to trick you into using the power rule and saying that this was 3 pi squared. But remember, the power rule only applies when the base is a variable. But pi is a constant. So this is really just a complicated way of writing a constant function. How would you interpret your answer?
As x increases by 1, the function does not increase.
Yeah, the function doesn't change. Is that true? Is it true that the function doesn't change?
Yep.
Yeah. What's f of 1? What is f of 1?
F of 1 is pi to the 3rd.
Yeah, and what's f of 2?
Same thing,
yeah,
pi to
so
the
the
3rd.
function really doesn't change. So it wouldn't make sense to use the power rule here because that only applies when the base is a variable. Okay, very good. Good, so you got that correct. That trick appears occasionally on the practice tests. Now let's take a look at another function. Let's do f of x is 3 e to the x. F of x is 3 e to the x.
Like that?
Sure, and let's figure out f prime of x.
Okay.
Okay, excellent. So we've already reviewed how to find e to the x. Again, you don't use the power rule here. The power rule doesn't apply because the power rule applies when the base is a variable. But here, the base is a constant, and the exponent is a variable. So we have a whole new rule for working that out. Okay, very good. I'll go back to my screen for a moment. Okay, let's try this.
X cubed minus 4x squared plus 5y plus 2x to the e to the x. Okay. Derivative, okay.
How did you get that negative 3/2 exponent at the end?
Negative 3/2 is minus 1/3 minus 1. So negative 1/3 minus 3/3 equals negative 4/3. Okay, now I'm going to plug this all into my calculator. Minus 8. Plus. Okay.
Okay, good. All right. Now, all right, so there was one mistake here. We made a mistake finding the exponent with the power rule. Now, I know you understand how to use the power rule, so the power rule here is just, it's easy to make careless mistakes, so it's important to double check each step. In this particular case, since the x was going to equal 1, I think we would have still gotten the right answer by accident, but if the grader was paying attention, they'd still take off credit for the work. Okay, so it's just important to double check each step here when there's a whole bunch of different parts put together in the same problem. But in any case, you had the correct conceptual approach for this type of problem. Notice here that we're basically using the sum and difference rules. We're finding, here we have the sum or the difference of a whole bunch of different terms. Well, all we have to do is just take all of the derivatives separately and then add or subtract them because derivatives behave naturally for addition and subtraction. Okay, I'll write down a problem on my screen.
Okay.
Okay, so let's go back to your screen then and work on this problem.
Okay. Okay.
Okay, good. So I noticed, so let's see, you wrote down that root pi is pi to the 1/2, and then you said its derivative was 0. Why did you say that derivative was 0?
Because it's a constant.
That's right. So we don't use the power rule on that.
Okay.
Okay, that's good. But given that that's the case, we could have made our lives easier. There's really no need to rewrite it as pi to the 1/2 power. We could just leave it as the square root of pi, because that's a constant too. So what you did was not a mistake, but it was an unnecessary complication that might confuse us. Okay, good. So let's work out what f prime of 3 would be.
Okay. So I'll just plug that in. Okay.
Okay, good, great. On the test, the instructor would probably prefer that we just leave the answer as e to the 3rd, since that's exact, but it was good practice to approximate it on the calculator as well. All right, now I'd like to show you a trick for that problem, so we'll go back to my screen.
Okay.
Okay. Let's see here. So, and do you have your calculator with you?
Mm-hmm.
So maybe you can follow along as we're going here. So let's press the math button.
Okay. Okay.
And then we scroll down to this. So your calculator can take derivatives. And it shouldn't be too hard to remember this is the option for that. It looks like derivative. And then the derivative we're taking here is e. Here's the x button, e to the x plus square root pi. So try typing that in. Don't hit enter yet.
Okay. Should I press second log, or second natural log? Is that e to the x? Yeah. Okay.
You already used that key when you were just calculating the answer a second ago, didn't you?
No, I typed in e.
Oh, do you mean you use this e instead?
Right.
Okay, that's fine. Yeah, as we discussed a couple sessions ago, you can use either E key. It's a slightly different series of keystrokes, but so I happen to use the E over the natural log. But if you want to use the number E on the right-hand side, that's perfectly fine.
Okay.
So just tell me when you type that in.
Yep.
All right, next we have to hit comma. We have to tell the calculator what variable we're taking the derivative with respect to. So I hit X again. I think I need to do that. We'll see how that works. Then you hit comma, and then you have to type in the number that you're taking the derivative at. So that's 3. Let's see if this works. Then we hit enter. Is this the answer that we got?
Yeah.
Okay, see if you can get that same answer on your calculator.
Yep, I did.
Okay. Well, obviously, you can't just use this to get the answers on the test because I'm sure your instructor is grading by looking at your work. But this is still very helpful because it lets you it tells you whether you got the answers right? This way you can tell whether you got each answer on the test correct. You're allowed to bring this calculator to the test? Yep. Okay, so this means that you'll be able to tell whether you got actually each answer on the test correct. I think you said on the previous exam you had quite a bit of time left over at the end for double checking your work.
Yep.
Okay. Well, if that's the case on the next test, then you'd have plenty of time to go back and use your calculator to check each of the problems. That's a good thing to do because we've seen it's easy even when you understand the methods to make careless mistakes. And then you can diagnose that with the calculator and go back and check more carefully. These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you.